Here is a numerical type question. Work through the numbers carefully. Let us solve it step by step. Let us begin solving this step by step. Identify the product. The product shown is a cyclohexane 1,4-dione bearing to aldehyde, ChO, groups at C2 and C5, or equivalently positions 2 and 5 on the ring. This is 2,5-diformylcyclohexane 1,4-dione. Moving on to the next step. Work backward from the product using PCC. PCC oxidize primary alcohols to aldehydes and secondary alcohols to ketones. It does not overoxidize. Since 4 moles of PCC are used and the product has 2 ketone carbonyls and 2 aldehyde carbonyls, reactant A must have had 4 hydroxyl groups that were oxidized to secondary alcohols, giving the 2 ring ketones, and to primary alcohols, giving the 2 aldehydes. Therefore, A is 2,5-bis hydroxymethyl cyclohexane 1,4-diol, i.e., a cyclohexane ring with OH at C1 and C4, secondary, and CH2 of groups at C2 and C5, primary. This accounts for exactly 4 moles of PCC. Moving on to the next step. Count the OH groups in A available to react with AC2O. AC2O acetylates hydroxyl groups and any other nucleophilic OH. Reactant A has 2 secondary alcohols at C1 and C4 of the ring. 2 primary alcohols, the CH2 OH groups at C2 and C5. Total OH groups is equal to 4. And for the final step, each mole of AC2O acetylates 1 OH group, 1 equivalent of AC2O per OH, consuming 1 mole of AC2O per OH. Therefore, 4 moles of OH groups require 4 moles of AC2O. Check for any other nucleophilic sites. There are no amine groups or other readily acetylatable functionalities in A, so the maximum number of moles of AC2O consumed is 4. Therefore, the correct answer is 4. Therefore, the correct answer is 4.